Yeah, so welcome on our DataOps Poland meetup. And today, Yugabyte, the distributed SQL database. So welcome on our stage, our guest. Frankie, you can share the screen and I'm stopping. You are star right now, so stage is yours.
Okay, let me share my screen. Sharing this one. I have slides, I have demo, and yeah, I'm Frank Pachot. I'm developer advocate for Yugabyte. I've been working for more than 20 years on databases, mostly as a consultant and a lot on commercial databases. I've started with DB2 and a few Informix, Sybase, but a lot of Oracle. And then a bit of Postgres and really interested by the open source and wanted to know also what is new, what is coming in the database area. And I was so interested by YugabyteDB that I became developer advocate for Yugabyte. Developer advocate basically for me is like being a user but paid to use and improve the product with feedback and all that. So it was quite a big change from consulting, but finally it's mostly the same, just helping users and getting feedback. So what I will do is presenting what is Yugabyte, but the goal is more to put some information about distributed SQL, because those are the new databases that are raising. I will have a small demo about the most important feature for me, which is resilience. And do not hesitate to interrupt me if you have any question in the chat. The goal is really to adapt the content to your questions also, because I can go very deep in technical things, but probably an overview is better for most of you. So we will do as your questions are coming. Already talked about myself. I have an email. I'm a lot on Twitter. I have a blog, and yeah, and quite easy to find and to reach me if you have any question, feedback. Do not hesitate. I'm just looking for the window where I can push next. Okay, yeah. So basically, in short, YugabyteDB is a distributed SQL database, and I will define that, how it is different from the SQL databases that we know. Fully Postgres compatible, and I will also explain what makes it compatible with in the architecture, because basically it reuses a part of Postgres so that it can provide all features. And it's fully open source, which is quite interesting. Also open source like Postgres. I will also explain there are also other API, like a Cassandra-like API, but the most interesting, in my opinion, is the Postgres one, because we really have all SQL features there. And first, why being Postgres compatible? Because today Postgres is rising in popularity in the domain of OLTP, in the domain of SQL databases. This is you probably have seen this DB ranking engine. So be careful. It's just popularity measured on how it is popular on Stack Overflow and blogs, all that. So it's far from saying which is the best database or anything, but basically the most popular databases are Oracle, MySQL, and SQL Server. So two commercial databases, one mostly open source. Postgres is raising, and MariaDB is also raising. Be careful, it's a logarithmic scale here. So if people want to replace commercial databases with open source, they can go to MySQL or they can go to Postgres. Today, if you build a new database, it makes sense to be compatible with one of them to enter the open source database area. MySQL is more used for website, for example, web server applications. Postgres is more compatible with the SQL standard and offers also many features that makes it more interesting for OLTP, especially what is called system of records, the OLTP that we find in enterprises. So yeah, most popular open source database for OLTP. And by OLTP, here I'm saying all OLTP application, just not a single use case that looks like OLTP. Also the best compliant to the SQL standard, because if you use MySQL, there are a lot of features, but it's far from the SQL standard. And why is it interesting to be compliant with the SQL standard? Just because today people probably have to learn many databases, to use many databases, and move from one to another, especially commercials to open source. And then the more standards we are, the easier it is. And the last point also with the choice of Postgres compatibility, there are a lot of features built in, but Postgres offers an incredible extensibility where there are a lot of extensions for special additional functionalities. And this makes it also interesting when the goal is to build another database, to change the storage, and perhaps use other things. So this is why Postgres is interesting today. In this DB ranking engine, I've chosen the big ones, and I also displayed the distributed SQL ones. They started with Google Spanner. I will talk a bit about this story later. But after Google Spanner, then there are three main distributed SQL databases. CockroachDB, which is Postgres compatible for the protocol and the syntax. TIDB, which is MySQL compatible, and Yugabyte, Postgres compatible, but really reusing Postgres. So those are the three in this domain. One that tries to be compatible with MySQL, and two others with Postgres. So then Postgres looks perfect if we want to move from commercial databases to open source. But there are a few things that are not so nice here. First, it is monolithic, cannot scale out. The database can run only on one server. You can connect only on one server. And this poses a problem when you have an high load and require a lot of memory, but also for high availability. If this server is down, you have to start on another server. So with a standby, this can be fast, but it's not immediate. So monolithic today is problematic for the database. Most applications can run on clusters, Kubernetes pod, containers, and now we want the same for the database. Also, Postgres has disaster recovery because you can have a standby database, but it's limited for high availability. Because even if you have this standby, when you have to fail over, you are never sure that you didn't lose some transactions. You have the risk of speed brain, like you fail over because you think the primary is not accessible, but some people are still using the primary, and then the two databases are updated, and then you will have conflict. And also Postgres is quite hard when it comes to upgrade because that takes long. And Postgres has all the big problems that are there for years and years and not really solved, probably because the Postgres community focuses more on the SQL features, but also it's not easy to change something that is in the core that is at a storage level because there is a risk to break things. If you used Postgres, you probably know about table bloat. and the need to vacuum. And if you do not vacuum, the size of the database increases, and you have the risk even that the database hangs. I will not go into the details if you have questions, but if you use Postgres, you probably have seen those many problems. So if we want a new database today, we want to be Postgres compatible because it is popular for LTP and compliant to SQL, but we want to solve what is in the storage layer for high availability and for those small problems that can happen. I will take another example, a commercial database. I take Oracle because I've been working a lot with it, and also because this is where we see most people who want to leave Oracle and go to open source, probably because of the price. In those commercial databases, you have a good high availability. In the case of Oracle, you have RAC, you have DataGuard. I will not go into the detail, but you can really provide high availability, like a server is down, the application continues, or you have a planned downtime to change some hardware on a server. You can do that without stopping the application for many cases. But it's still monolithic. So you still have one, even RAC is a cluster, but it shares the disk. So you have still something monolithic. Oracle is complex, and even if it provides high availability, because of the increased complexity, usually if you don't have a lot of DBAs to manage that, you have more problems than what the availability solves, and it is expensive. That's probably everybody knows, and it's not open source, and you are locked in, and people want to go to something else. So two traditional databases, one Postgres open source, one commercial Oracle. And then for the need to scale out came the NoSQL databases. So here the idea was that for some workloads, so for big companies, but then for a lot of web activity, running on one server is not sufficient for the resources, but also sufficient for the availability, sufficient also because we have users all around the world, and we cannot have them all connecting to one country with the latency. And also because people are moving to the cloud, being able to scale out also fits better what we can do in a cloud where most cloud providers have regions with free availability zones. So in your data center, probably you have one or two data centers in your company. In the cloud, you can have multiple availability zones. And this is where you have then the idea to scale out and not have just a standby just in case. So NoSQL databases, perfect to scale out because data is distributed, processing is distributed. And it's cloud native in the sense cloud native. In the cloud, everything can fail because there are a lot of resources, there is network, and you can have transient failures, you can have availability zone failure, you can have region failures. So need high availability for that. And also elasticity, because if you go to the cloud and you provision all servers for the peak activity, then probably it will cost a lot, even more than on premises. The goal of going to the cloud is also to be elastic, being able to run with low resources when you don't have a lot of activity and increase. And this also requires the ability to scale out, because scaling up one server is not easy. But NoSQL databases, to be able to distribute the load, had to remove some features that were there in SQL databases. That's why it's called NoSQL. So eventual consistency means that you cannot have consistent transactions, especially if the transactions are touching multiple tables, multiple rows. And the lack of many SQL features, all the features that many people may think that you can do the same in the application, like verifying the integrity, But if you do it in the application, you need a lot of code and a lot of tests to do that. Maybe I can add something about it. For me, the most important in having unique constraints, foreign keys, or all these integrity constraints in the database is that when the database provide them, the database has been tested to provide them even when multiple users are running concurrently. And then your unit tests are still valid at race condition when people are reading the same data, because the database manages the logs and the serialization of it. If you think you can enforce the foreign keys, the unique constraints in the application, then you need to test that. But testing the race condition where multiple sessions are updating the same data. So relying on the database not only to have less code, but less tests to do and more reliable. Okay, so the traditional SQL databases with a lot of features that have been added through 30 years. The NoSQL databases, which provide a way to scale out and distribute data. And now the convergence of that is new SQL databases. So the idea there is to be able to scale out with all the SQL features. So being cloud native, because this come at the same time in a shared nothing architecture, so not a cluster with a dedicated network to be run in the cloud. You need to allow any network and scale out, resilient in case of failure, and the same scalability. So NewSQL was a term originally for distributed SQL databases, but because there were a lot of other kind of distribution, then NewSQL today is a term that covers all databases where something is distributed. Like Amazon Aurora, you still have a single database instance where you connect for reads and writes, but the storage is distributed. And you have also read replicas where you can read, even if it's not in inconsistency with the one. Google AlloyDB is the same. They kind of copy Aurora and provide more features because they do that a few years later. I didn't mention it in Postgres area. There is also NeonDB doing something like an open source Aurora. So this distributes storage, but not transactions. You cannot have a transaction touching data on different nodes. And then this is where distributed SQL comes. And that started with Google. So Google had many NoSQL databases, especially Bigtable. And they realized that, yeah, it was good to scale on their cloud on multiple regions. But at some point, because in NoSQL, you don't have all those features, you have to put them in the application, and then evolving this application is quite difficult. So this is where Google tried to keep the same idea of data distribution and add some SQL features on top of it. At the beginning, it was very limited SQL, but they started then to implement foreign keys and secondary indexes and all that. But Google Spanner has something very special to be able to have performance, high performance in a cloud where you have latency between the nodes. They use atomic clocks in their data centers and communication by satellite to synchronize the clocks of all servers, which means that it works only on Google Cloud. Then CockroachDB started to do something that can run something similar, but that can run on any platform. So not dependent on atomic clocks. So maybe not the same high performance as Google Spanner, but being able to deploy that everywhere. And they have chosen to use the Postgres protocol and to they really build a new database, but the SQL, they make it like Postgres to not to reinvent something. It's not fully open source. For example, in the community edition of Cockroach, you cannot do backups. And then a few years later, Yugabyte started on that with the idea that we will need all SQL features on those distributed SQL databases. So instead of doing like Cockroach, adding SQL features like Cockroach or Spanner, adding SQL features on top of the distributed storage, the idea of Yugabyte was like, we will need all the features that are currently in Postgres, then just let's take Postgres and plug that on a Spanner-like storage. So that was the idea. And being Postgres compatible, also fully open source. So I will come back on the architecture of it, but it's quite the big innovation there is to plug Postgres on top of a distributed storage and then optimize something rather than starting to put features one after the other. So basically, but that's just a summary of what we have seen. Architectural resilience means that we have availability, we have resilience from the architecture, not with added layers like a standby database, scaling, and geo-distribution, because when you can scale out to multiple data centers, this can be in the same zone, but also in multiple regions. And then you go to geo-distribution because some of your data may have to be located in Europe, for example, for legal reasons, or to be close to the users with full ACID transactions. So that's the goal of the future databases, or of the distributed SQL databases. Basically, the monolithic databases, as we have seen, have ACID transactions SQL. The NoSQL have all this resilience, scaling, geo-distribution, but they miss the other, and the idea of distributed SQL databases is really to provide all of them. It's still work in progress. I mean, it exists and it exists in production, but there are still improvements on it to have more features and better performance. Really, those are the databases which will raise in the coming years, in my opinion, but that's a general opinion also. So just about Yugabyte, it was founded by the people who have been working on Cassandra and Database at Facebook. So they have a quite good idea about SQL and NoSQL, because this is why Cassandra and Database were created. And they started on the Google Spanner paper, so same architecture, adapted to something that is not linked to a specific cloud. And so that was 6 years ago. They started with the transaction and storage engine, so called DocDB, and with a limited API, which was more like Cassandra for the first customer moving from Cassandra to Yugabyte. So same API, same syntax, but fully consistent, fully ACID. Basically, the code for that RocksDB was used for the different shards, and on top of it, for the replication, the Raft protocol. I can come back after with more detail about that, but the consensus protocol based on Apache Kudu, but with a lot of innovation. And then 3 years later, this is where they plugged Postgres on top of it. So it's a fork of Postgres that is plugged there, but here the goal is really to follow the versions. So a fork where new versions can be merged to follow the version of Postgres for compatibility, and also to benefit. Postgres evolves a lot with all the features in the SQL layer, not a lot in the storage layer, but here we have a different storage. Basically, you can think about those two layers. The Postgres layer is stateless. It processes all the SQL, but when it has to store or read some data, then instead of storing in local files like Postgres does, it interacts with the lower layer, the distributed storage, to get data from the different nodes. And I will show quickly the architecture, as I mentioned, so those two layers, you see them here, the distributed transactional and transaction storage layer, and on top of it, Postgres. Actually, the architecture allows many APIs. As I mentioned, it started with a Cassandra-like API, also because the first customers were moving Cassandra application to then go to SQL. Now the mostly used is the SQL API from Postgres. Maybe one day, if people need it, MySQL API can be plugged on top of it. But for the moment, this probably sufficient. The storage, not only the storage is distributed, but the transactions means that transactions can span multiple nodes. Load balancing, that's automatic rebalancing of data. Data is sharded. The tables and indexes are sharded, so partitioned to be distributed. And replicated also for high availability, and the replication is done by the Raft consensus, and all that can run on any platform, basically. A VM, a pod, a container in the cloud on premises. Can be also hybrid. You can also have 2 data centers and one in on the cloud. For the replication, because of the Raft protocol, you need basically most of production run with a replication factor 3. The goal is to have a quorum, but I can explain that a bit more later. The idea is to have a quorum, so that's when one node or one data center on one region is down, then the other can elect the new leader that is consistent. And if you have no questions, I will do a very simple demo, and maybe some questions may come. So I've put that it's quite easy to run on Docker on a laptop, and this is what I will do. So I'm on Windows. I have Docker desktop here, and you tell me if you want me to increase the font. I think it should be okay like that.
I think it is okay.
Okay, perfect. So if you can, of course, run one node, but the idea is to see how it works with multiple nodes and when one is down. So in Docker, I create a bridge network, and I will run a first pod, a first container. So calling Yugabyte, this is the latest version, and I put a host name. I will start 3 nodes, YB 0, 1, and 2. And just one command that starts. I publish 2 ports. One on 7000 is a little grid that we will see. And the other 5433 is the Postgres endpoint. Postgres default port is 5432, and we use 5433 here for that. So for the moment, I have one node, and I will look at this port 7000 to see what happens there. So yeah, it's already there. So here I just say that I have one server and one server there, YB0. And I will start 2 others with a very similar command line. The only difference is, of course, the name, YB1 for this one. I use another port to connect to this one, because this is a distributed database, which means that we can connect to any node, and then there is a Postgres endpoint on any node, and we see that as a whole database. But the big difference with the second command is that I join the first one, so that this forms a cluster. And then if I come back to the GUI of the first one and I refresh, I see the second server there and alive, and I will start a third one, YB2, to have the most simple of 3 nodes cluster. So basically in the GUI, in the home, we see the master, which holds the metadata. For the master, you need only 3 nodes for the redundancy. For the tablet server, which really stores the data, we can add more nodes, and we will do that later. The minimum is the replication factor, so that everything is replicated. And if one is down, we can have a quorum from them. And for the moment, I have no table except system tables, which are the Postgres system tables. Okay, then I will show you that we can connect to any node. So I connect with PSQL, the Postgres client. On the port that I've redirected for the node 1, the YB0. And I can also see all the nodes from there with a special view, YB servers. You can see that there is a mention that I didn't use it there, but when you start a server, you can mention on which cloud, which region, which zone it is. Because the goal is to be able to have redundancy at zone level, region level, or cloud level. Those terms are for the cloud, but zone can be also your on-premise data center. But you can also run a cluster on multiple clouds. There are users doing that. Of course, it has a cost for the interconnection between the clouds, but it has other advantages. Sorry, I've clicked on something that listed everything. Let me reconnect. What I wanted to show you is that here I'm connected to YB0, and if I connect to another port, I am on the other node, YB1. So just that from any endpoint, any server, I can see the whole database from there. And I create a table. I create first an extension because I generate some UID. That's also the advantage of being Postgres compatible. There are a lot of extensions that just come like that. So I create a simple table and an index on it. And I insert some data. So I insert just one row where I also show from where I was connected when I inserted, to really show you that all nodes, you can write when connected from any nodes. So inserting some rows there, and from any node, I see, of course, the table, the whole table. So with rows that have been inserted from many connections to many nodes. Okay, and I will run. Maybe first, because before running it, well, I can run it. I will run the same in a loop, just to get some basic activity on my cluster, and showing you. So here, if I refresh the list of tables, I can see my table and the index that I've been created. And from this grid, I can see very short information from short information from the sharding. I'm just looking at the shortcut here. Oh yeah, no, was there just to make it shorter there. Yeah. So this is my table, the table that I've created. The type is PostgreSQL, because there are multiple APIs. It's important that we know from which it is. Information about the placement. I have 3 replicas. Only one place here, because I didn't define different zone or different clouds, but this is where it can be defined. And most important, I see that I have 3 tablets. So that's the default. I have 3 servers, so the tables were sharded to 3 tablets, 3 shards. We call that tablet. And each tablet here, it is sharded by default by hash. We can also shard by range. Basically, a hash function is the best to distribute, but this table, the sharding, the table is stored in the primary key, and I will have also indexes. If I query only with an equality, then hash function is perfect. But if I query for ranges, for example, ranges of dates, then I want to run sharding for that. So this is a choice that we can have during create table. And each tablet, so each of these shards that holds part of the rows, have a leader and 2 followers. This is the replication factor of 3. Each one have a leader and 2 followers. The idea is that all reads and writes will go to the leader to be sure to read something consistent. The follower is there only in case the leader is down, so for high availability. And when you read from the leader, you just read from the leader. When you write to the leader, it waits for one of the follower to acknowledge, to get a quorum. Why? Because if one acknowledged, then we know that if the leader is down, one of the follower has the latest values. So this is sync replication, but with a quorum. There are also some possibilities to read from the follower for reporting, for example, to avoid some latency. Let me look at the question. Followers are connected to the master. Yeah, the terms are not really easy. Master is just like another cluster for the metadata of the cluster. So master doesn't mean that it is master in the sense of replication. Master is just a catalog for all that. Each tablet is quite independent here. Means each shard is like its own database that is replicated, small database, not depending on the master. I will come back with a diagram later if we have time. So for the moment, important also to see that the leaders are distributed because we do a lot on them, read and writes. We want to distribute the load. And I can see that if I go to the tablet servers, I see my 3 servers, and let me see if and for all of them, I have the read and write operation. I'm doing only inserts there. So those are write operations, and they are distributed because I generate random ID. They are distributed with the hash function on the 3 tablets there. If I refresh, yeah. Now, so this is running. I will add more servers. Minimum is 3, but I can add more servers just to distribute more. So this is a loop that starts new container joining the existing cluster. If I refresh here, I can see that I have more server there. And quickly, I will see that they will take some writes again. Let me refresh, yeah. So some of the new ones, YB4, 3, 5, are now taking some writes. This is the automatic rebalancing. My demo table here. Now I can see that I have some followers on the new servers, even a leader on the new server. So this is automatically balanced. This is the elasticity. You have a peak of activity, you add new servers, and automatically the database will distribute that. Someone is saying that he cannot see the presentation, but others can. So yeah, I don't really know. I will explain what and it is recorded anyway. So here I can see, I didn't show, maybe I can show the index. The secondary indexes are the same, also sharded, of course, on a different key. For example, I've created the index as range there, and then I see that it's not a hash, but a range between values. I have text, and this tells me that this tablet will hold values between O and W. And again, leaders distributed, followers distributed. Okay, so we have seen elasticity. And now what happens if if one node is down? Thanks to the replication factor, I know that I am resilient. I will choose even one where I have a leader. So for example, I have a leader on YB1 for the second tablet here, and I will just Docker pose it. YB1. I pause it. Let me quickly show the application. I want to be fast. Yeah. The application is stopped for a few seconds and then continues. What happens here is that first, the application was waiting everywhere. So was also waiting on this leader that was in YB1. But first, leader wasn't there. So one of the follower has been elected the new leader. If I refresh now, this is my laptop, but yeah. If I refresh now, I think it was this one that had his leader there. But now one of the follower, they discuss, they vote for the new leader because they know that one of them has all data. And this happens in 3 seconds. We have seen a few more seconds in the application because there are TCP/IP timeouts that we can set also, or depending on the deployment. And can see that also in the list of servers. This node is marked as dead. We can see there are heartbeats between the nodes, of course, because they must know that they are all there, and also they must synchronize their clock. This one didn't reply to heartbeat for the last 70 seconds, of course. It's written dead, but it's not really dead because you can see that I still have the followers there. By default, it stays like that for 15 minutes because usually those kind of errors are transient. It will come back, and then this one is a follower but with a gap. It's not a problem because we need the quorum for writes, and then the other one can acknowledge the quorum. And this one, if it comes up, will catch up the latest changes. But the idea is that it's easy to catch up the last 15 minutes. If it's more than that, then better we start as if it was a new node. So here, if I have, I didn't expect my application to be hanged here. I don't know exactly what I did. No, that's fine. What I wanted to do it was to start it again. And then look. So I start the YB1 again. If I go to the server, now it answers to the heartbeats. And for the moment, takes no writes. It just has to catch up with the latest one. And maybe the cluster may move a leader to YB1. It's not the case here because everything is balanced, but to rebalance it, this can happen just electing it another time. I don't have enough tablets to see this. Maybe for the index, is there something in YB1? Yeah, for example, you see this tablet of this index, of course, was not a leader in YB1 when it was down, but now that it is up, it catches, it is a follower, and then this is where the master rebalances thing. The master says, oh, I have too many leaders on this, no leaders on that, and rebalances it. Okay. That's mostly what I wanted to show as a demo, but later, if you have more questions, we can come back to it. I will quickly explain. So this is what we have seen, the endpoint, the GUI. And I will just explain quickly what happens when the application is connected. So each node has a stateless Postgres where application can connect. And with the Raft protocol, it will send the writes and read from the other servers, the same server or the other servers, where the tablets are replicated. The idea is that this tablet has a leader here, follower there. This one is leader there, follower. Yeah. So if you are connected to node 1 and you write, and this writes to multiple leaders, and it waits for the quorum. If node 2 is down here, this application connected there doesn't even see a change because it's not connected to the node that is down, and it's not currently reading or waiting for it. So just transparent for many connections. The only thing is that the leaders that were there are elected leader in another node, so that when someone wants to read or write to it, it can. When the node is back, simply it catches up with the latest change, and then the followers are ready to be elected leader if it's useful to rebalance the load. Now, a case where I have the same application reading and writing to node 1 and 3, but 3 is down. So no leader there, I cannot write to there. This application has to wait that this one has a leader election elsewhere, which will happen there. And this is what we have seen, why the application was hanging just a few seconds, because a write on the node that is down had to wait for the new election. And the third case, because we can connect anywhere, maybe the node where we are connected is down, and then, no surprise, we have to reconnect. But usually you have a connection pool, and then it can reconnect to another node. And when you are connected, the leader election has been done, and you continue to working like that. Okay, I see that we nearly did 1 hour. I have some slides with more detail, but it may depend on the question. If someone has a question or remarks, or if someone knows other distributed database and want to compare.
Yeah, before we start, we have already the first one, Piotr, but I will be the first one, okay? So what about the performance? Can we test it like in normal Postgres, I mean pgbench, and do some test?
Yeah. So for performance, there are a few things to take care. First, you define the primary key so that it is distributed. The problem, if you run pgbench this, pgbench simulates a bank application and updates customer account data, but also updates a sum per branch, I think it's called like that. And of course, when everyone updates the same row, then you may have a contention. So for this kind of thing, this is where it's better. I mean, if you distribute, but your application always writes to the same row, then you do not benefit from the distribution. So need to be careful on the schema. For example, if you want to scale it for pgbench, just instead of storing a value for one branch, you can have multiple ones. So that's one thing. And the other thing, it will depend on the deployment. Of course, as we see there is cross-node communication. So then it depends. Those nodes can be on the same data center, can be on the same region. For example, on AWS, the latency between availability zones is 1 millisecond. From the latency, I cannot make a difference in AWS between 2 availability zones or 1. It's 1 millisecond. So that's probably okay for many applications. I've been working with databases at a time where reads and writes to disk were multiple milliseconds, so that's fine. Of course, if you want to do geo-distribution, then you have to think about the latency. Because if you update 1,000 of rows that are distributed in all countries, and you wait for the quorum on that, then it will take time. And for geo-distribution, I can show you, I have a slide, maybe about geo-distribution. I'm not sure where I have it. Yeah, just to give the idea. So what can be done? For example, this is an example where you have a primary cluster on 3 availability zones in the same region, so low latency. But to be able to do some reporting from other regions, we can have read replicas. Read replicas are kind of followers, but they do not acknowledge the quorum. So you have a replica that is asynchronous, basically. You do not want to acknowledge the quorum because you do not want, even if something is down in the primary region, you do not want to wait 100 milliseconds quorum for that. So that's a choice. And there is also another choice. You can also, by default, all data is distributed on all the cluster. If you do some geo-distribution, I don't know if I have, no, I don't have a diagram, but for example, you can put nodes in sync in the quorum in multiple regions, but then you can also tag some regions to have the preference for the leaders. You have seen that all the writes are going to the leaders, and then maybe you want to put them all at the same place. And you can also do that for different data, so for different tables, for example, but even for different table partitions. And there, I'm not talking about the sharding, but the partitioning like we have in Postgres. For example, I am a bank, I have customers in Europe and in US. I want to store my customer data in Europe for European users, in US for US users, for 2 reasons. First, because there are laws that force me to do that. And second, for the latency. Mostly, the European users will connect from Europe. So if their data is in Europe, latency will be okay. If they travel, maybe the latency will be higher, but they will understand because they are far. So this is how we do when the latency is high. We cannot change the speed of light, but we can change the placement of data so that we do not have to wait for this long latency for most operations. So that's basically how the latency is done. But something else I should mention, if you compare, even if you run a PG bench without this single table where there is contention, even if you compare, if you run Yugabyte in a single node and run Postgres in a single node, it will be faster in Postgres because Postgres will write a lot in local memory. The architecture of Yugabyte is that there is some communication with another layer before storing in memory. So basically, if you want to run in a single node, it's probably not a good idea to go to a distributed database. When you want resilience, if you add a sync standby to Postgres, you will start to see some latency, and then the difference in performance will be similar finally with the degree of protection. So that's the idea. If you don't need to have more than one node, you will be faster in Postgres for sure.
Okay, thank you. Piotr, sorry for that. I thought it will be quick question.
No, but it's really important. I can also add something. For the moment, it's mostly optimized for OLTP. For data warehouse, it's possible, but it needs more optimization because when you do some aggregation, you don't want to read from many nodes, send them to the one where you are connected and aggregate there. Needs to push down a lot of operation that is not yet been done. For the moment, it's more OLTP. So that's another thing if you are doing data warehousing, probably better either to go to a single node Postgres or to Citus DB, for example, that shards without global transactions, but with more pushdowns.
Okay, so Piotr, your turn. Just unmute yourself.
I hope you can hear me.
Yeah.
Yeah.
Okay. So the first question then is how new PostgreSQL lays under the YugabyteDB? Is this Postgres 13, 14?
For the moment, it's compatible Postgres 11. It started with Postgres 10, and then they merged to Postgres 11, mostly to see, it was kind of prototype to see how it is easy to merge or not. And then the engineering decided to stay on Postgres 11 compatibility because a lot of new features were added and not good to do everything at the same time. The goal is end of the year to be Postgres 13 compatible and then really follow the versions.
Second question about what is performance difference between, for example, three instances of nodes with Yugabyte and one instance with PostgreSQL? Does it?
That's difficult to say. You can see 2 times longer. You can see 10 times longer. That's the ballpark. Really depends. Yeah.
I mean, in massive operations, yes. I do not mean just single SQLs, but massive operations,
Okay,
which
yeah.
are huge tables. So
the idea is the speed, the response time of one query may be longer on a distributed database, but you can scale more. So you will see the advantage because you can. It will be difficult to have transaction to less than 1 millisecond, for example, where in Postgres without sync replication you can because you write to memory. But then you can also scale with many nodes, and then the number of transactions per second can increase.
So does it work like Elasticsearch? So when it will be on the one node, it will stop to receive the right commits? Yes. Because in Elasticsearch, when it is standalone, when it stays alone in production, it stops. Yes.
So here, if you have a replication factor 3 over, let's say, 3 availability zones, so maybe you have 10 nodes in each availability zone. If you have replication factor 3, when one zone is down, everything continues. But if a second zone is down, you don't have a coron, and then it stops because it cannot guarantee to get the latest data. Yes, if you want more resilience, you can run in replication factor 5, where each tablet will have 4 followers, and then 2 of them can be down, and you still have the quorum.
How is solved data consistency within the situation when one node updates data because it received update message, and another one at the same millisecond is being asked for the new version of data? So update and select.
So that's about clock skew.
Yes.
Yeah. The physical limit of this kind of thing is that you are never sure that all servers have exactly the same time, and you need the time to order the transactions.
But is it any mechanism which serves, for example, the newest hash data?
So there is a mechanism to avoid the problems, because each time where 2 servers communicate through heartbeats or because they have to communicate, they synchronize their clock with a logical time. So it's a hybrid clock with a physical time and a logical time using the Lamport algorithm. But you may still have a case where one server is not synchronized, and then your transaction can see it. Means that when it reads the commit time, it reads it and it says that there is uncertainty in the time that is within the accepted clock queue. And then you get an error message. Same error message as when you have a deadlock or something that's where the database cannot run your transaction. It's more like cannot run the transaction, start it again.
Understood. So the transaction should be repeated. Yes, the select should be repeated.
Yeah.
And the last of my questions, Postgres.
So the Postgres extension for the moment is not supported. Basically, being Postgres compatible for this SQL layer means that the extensions that are on that layer are easy to get working, but those that touches the storage have to be implemented differently. For example, for the gene indexes, we support them, but with a slightly different implementation. And the GIST indexes are also in the roadmap, but not yet there.
Okay, thank you.
I will add something about the transaction and the clock queue. Usually in distributed database, you run in serializable isolation modes where the application must have a retry logic. The idea is that if you want to distribute, you don't want to wait. So you just run the transaction. And if there is a transaction conflict, clock queue, or just because you are doing things concurrently on multiple rows and the same rows, so the application must be prepared to get a serialization error and retry. So most of distributed databases do that, Google Spanner, Cockroach. But because Yugabyte's goal is to be Postgres compatible, and most of Postgres applications are using the default isolation level that is read committed, we have also implemented read committed so that there are no serializable errors. And in that case, if you are in read committed, even if clock queue is detected, you will not get an error, because in read committed, the database can restart itself what has been done. But that's only when you are read committed, because in read committed, you can restart at statement level, not restart the whole transaction. So it's possible to avoid all kind of errors that necessitate a retry logic in the application, just because a lot of applications written for monolithic databases do not have that. If you want more performance, probably better to go serializable for some things, but it works, yeah. Any more questions?
Yeah, guys, it's your time. So if you have anything, just use the raise the hand button. And
well, if there are other questions, I've put a lot here. We have a community Slack channel, so do not hesitate to go there if you test it. And I'm also, I said a lot of on Twitter.
Yeah, you also have the free T-shirts and stickers.
Exactly. Yeah, when you install it, you have a link to the community site. Can I